That's perfect. I will share. Do you see the slides? Do you see it?
Yes.
Okay, so I will
Mhm.
start. Good morning, everyone, or good evening, wherever you are joining us from. I'm Mary Salvana, Assistant Professor in the Department of Statistics at the University of Connecticut. On behalf of the organizing team, I'm pleased to welcome you to the Spatial Temporal Statistics and Data Science online seminar series. This series brings together professors, researchers, practitioners, and students worldwide to explore methods, theory, and applications of space-time data. Our goal is to provide a platform to share ideas and to spark conversations that push the field forward. We're grateful for the support of the ASA section on statistics and the environment, the Royal Statistical Society's Environmental Statistics section, and the International Environmetric Society, or TIES, whose communities help broaden the reach and impact of this series. Each seminar runs for 60 minutes. The speaker will present for 45 minutes, followed by 15 minutes for questions. Please feel free to type your questions into the chat at any time. We will collect them and raise them after the presentation. All talks are recorded, and the recordings, along with the slides, will be posted on our website. We host one seminar each month, and you're also welcome to nominate future speakers. To stay updated on upcoming events, you can subscribe to our mailing list, and you'll find those details as well as other resources at sdsds.org. With that, I'm very glad to introduce to you our speaker for today. Dr. Yan Gong is currently a visiting assistant professor of statistics and data science at Mohamed bin Zayed University of Artificial Intelligence in Abu Dhabi. Before joining MBZUAI, she held postdoctoral positions at Harvard T.H. Chan School of Public Health and Imperial College London. She received her PhD in statistics from King Abdullah University of Science and Technology in Saudi Arabia. Her work spans statistics of extremes, spatial statistics, and causal inference. With that, I'm happy to turn it over to Yan to begin her talk. So go ahead, Yan.
Mhm. Thank you, Mary, for the introduction, and thanks everyone for joining. Sorry for waiting. There was some technical issue for sharing my slide. So today I will present my work on causal spatial quantile regression. It's a joint work with Ritam from University of Arkansas and Brian from North Carolina State, and my PhD advisor, Raphael Husser from KAUST. So I will first very briefly introduce my research and dive into this topic. So I think of myself as an applied statistician, and my research is always motivated by developing and applying new advanced statistical methodologies to address complex and real-world problems, including challenges in financial risks, extreme weather events, and public health. From my PhD, I have been start to work on extreme value analysis and risks, including risk modeling and inference, risk prediction, risk monitoring, and generative modeling. And today, the topic will be on the second direction, moving from statistical analysis to causal inference, from focusing on the tail to the whole distribution. So it's on spatial causal inference and distributional treatment effect. And another direction of my research, which I started since my postdoc, is on biomedical imaging modeling, which is also basically spatial data, particular for human microbiome biofilm imaging analysis. So today the topic will be on spatial causal inference and distributional treatment effect. Our paper was on arXiv since later last year. And in a very wide range of applications, including economy, environmental, and epidemiology analysis, the treatment effect often vary across space. and understanding the heterogeneity of the causal effect across the whole outcome distribution and quantiles is a critical challenge in spatial causal inference. And this work in particular, we have several contributions. Basically, this framework is the first in the statistical literature, which can effectively identify the spatial heterogeneity in distributional treatment effect, which means across all the quantile for the whole distribution. Secondly, the framework is semi-parametric and neural network based. It's highly flexible with very fast computation also. So it can capture complicated dependencies, including nonlinear, high-dimensional, and complex interactions between covariates. The treatment effect here is also able to identify the heterogeneity inherently, including the nonlinear and spatially varying and tau-dependent quantile treatment effect. It can be estimated within our framework with relatively low bias, and our methodology is validated by both simulations studies, and it was applied to analyzing the causal effect of maternal smoking effect on the outcome of babies' low birth weight. The data is from North Carolina. Next slide, please. So I will introduce the methodology. So from the beginning, we want to build the spatial quantile model. Basically, first, let's introduce some of the notations. We have data, which is denoted as the big O. We have Y, T, X, and S, where Y is the response of interest, T is the treatment variable, X is a vector. It includes all the covariates we are able to capture, and the S, which is notated as a spatial, so it's related to all the spatial coordinates of the observations. And there's a small remark that both of the observed covariates and treatment variables can be either spatially dependent or spatially independent. And our approach integrate the spatial dependency and distributional heterogeneity by leveraging two of previous good work, including the deep kriging, where they use deep neural network architecture to optimize for the spatial mean prediction. And another framework is for the semi-parametric quantile regression, which is a flexible framework that models the conditional quantile, use monotonic splines with neural network-based weights. Next slide, please. So how do we build our spatial quantile model? Based on this SPQR framework proposed in 2021, the spatial density, the conditional density and the cumulative distribution functions can be approximated by a finite mixture of shape-constrained splines. In particular, we use M spline and I spline. These splines has very nice properties, and with this type of construction, it will behave like a CDF and a PDF. So we can approximate the density and CDF very well in this framework. And in particular, as it's highlighted, this theta k of T, X, and S, they are the mixture weights. And we require them to satisfy the following conditions. They need to be greater or equal to 0, and the sum equals to 1. And in particular, these theta are modeled by neural networks that introduce the flexibility. Next slide. So we want to leverage the flexibility that we can build based on the neural network. So in particular, we use a softmax output activation function for theta. So you can see theta is modeled with the exponential weight, and it includes also this weight matrix, which is denoted by W. For the architecture of this neural network, it doesn't have to be many layers. With probably 2 layers is flexible enough because there's already many parameters inside. And in addition, to introduce the flexibility or capability in the spatial setup, we introduce multi-resolution spatial features, which is denoted by the big I's. So we use a group of one-light type of functions, which is multi-resolutional spatial features, which was also used in the deep kriging framework from the paper 2024. So we include the spatial features and the neural network-based weight functions. In the end, we could model our conditional CDF function directly, and by just inversing the CDF, we will get the whole conditional quantile function at each of the quantile of interest we would like to, and we model the whole distribution, so there will be no crossing problems, which is related to the quantile modeling. Next slide. So first we build our spatial quantile modeling framework, and now we want to define what is the spatial quantile treatment effect, where we call it SQTE. So for causal inference, the identifiability for causal effect usually require standard assumptions on observed responses, treatment, and the covariates. Sometimes they are testable, sometimes they are not testable. And here we are listing a group of standard causal assumptions. In particular, we emphasize that we want to assume there is no interference effect, which is a common scenario in spatial setup, but here we are making quite strong assumptions on this non-interference effect. And also for the assumption 3, which is also a quite strong assumption in causal inference, which is assuming there are no hidden confounders. And actually, we do require the assumption of ignorability, but actually in our simulation, we test there are several cases where we can relax a little bit of the ignorability assumption. And the other assumptions on the unit treatment value assumption, one version of treatment, and the consistency positivity, they are standard causal inference assumptions that we also require. And these 2 highlighted assumptions are what we need to pay more attention for spatial causal inference particularly. Next slide. So in the context of this work, we do assume all of the assumptions hold, which are a little bit strong. And the assumption 3, which we require there's no hidden confounder, is usually violated in real life and untestable. So as I mentioned in our simulation study, we do include one scenario where we have hidden confounders, and for some of our techniques, we can relieve a little bit of this effect. So building upon all the assumptions 1 to 4, the spatially varying and tau-dependent quantile treatment effect can be defined as the difference, the expected difference of the quantile functions, where we use this notation like assignment for t. So we set t equals to 1, which is let's say is the one of the scenario, and when t equals to 0 is another scenario, either it's factual or counterfactual, and we are calculating the average difference from these two scenarios. So delta is dependent on tau and s, and our SQTE is basically defined in this way. In particular, if we want to write it in the integration format, we can also assume the density measure for x and write it in the integration format. Next slide, please. So for the estimation of SQTE, we use one type of the causal estimator, which is called the plug-in estimator, and it can be estimated in the following format. Basically, here we are using a simpler version of the notation. Before we were assigning t equals to 1 and t is equals to 0, and here we are just putting the treatment scenario on the top of Q. As you see, there's Q1 hat and Q0 hat. And this will be our estimator, which is one type of causal estimator, which is the plug-in estimator. So in this way, we can calculate the delta height for quantile tau and the spatial location P, SP. If we only care about quantile treatment effect, we can do a spatial averaging operation. So we can also get a tau of delta of tau by basically doing calculation over the whole space and the average for the effect. So in particular, in our case, for the application, we care a lot about a very low quantile. So the tau height, we are written down in this format. Next slide, please. So we run a large-scale simulation in several scenarios, and here is a general setup. So basically, we are simulating data on a regular grid over the square 0 and 1, and the number of locations is 400. At each of the location, we generate 1,000 observations from 5 different models, which we will introduce later, and 3 different scenarios we will introduce in the next slide. And in all of the scenarios, we conduct our simulation, and we repeat our simulation for 100 times for each of the model and each of the scenario to quantify the uncertainty. And in particular, our framework works only for the binary treatment scenario, and the binary treatment variable is generated or simulated by the Bernoulli probability. So we are giving different type of probability function for the parameter p of s. So it can either be spatially dependent or not. So it could be dependent on s or not. And so the probability is belong to 0 and 1 is the probability of receiving the treatment at location s. And sometimes in our the last scenario of our simulation, it include even the hidden confounders. So this is the general setup. Next slide, please. So we simulate 6 different type of observed covariates. So we say the observed covariates which are not hidden. So we can have data observations for them. And they can be either spatial or non-spatial. So you can have a look at x1 to 3, they are non-spatial, and from x4 to x6, they are spatially varying covariates. So we are simulating different type of covariates, which can be univariate, following Gaussian distribution, binomial, or for the spatial covariates, we are using the multivariate Gaussian in our simulation, and which is also a stationary Gaussian process with one parameter lambda, which control the scale. And we are choosing different lambdas for x1, x4 to x6. Next slide. So those are observed covariates, and we also simulate 3 different type of hidden covariates, which means they will influence the outcome or the treatment, but they are not measured. So in reality, you don't really know H. So hidden, H means they are hidden covariates. And we also simulate different type of hidden covariates. For example, H1 follows ID Gaussian distribution, and H2 is a spatial multivariate spatial Gaussian, and H3 just follows this oscillating function consisting sine and cosine. And our data generating mechanism can be written as follows. So the quantile of y is equals to a function of x, f of x, plus g of s and t, and the h of the hidden covariates plus the noise. In particular, we are writing down the format in a quite general form. So function f, g, and h, you can specify them as you wish. And the q is the quantile function. And so we are writing in this general form because we want to make them as flexible as possible. So you can choose your favorite choice of f, g, and h. For the noise, here we are just using a Gaussian distribution with the mean equals to the sine plus cosine function, and the variance equals to 1. So this is our data generating mechanism. Next slide, please. And we consider 5 different type of models. The first one only include the covariates, so we will only use the covariates to fit the functions. And second one, not only the covariates, we also include the spatial coordinates. And from model 3 to 5, we are including spatial features, which we basically use multi-resolutional spatial spline functions, which we include in our modeling. And here, if you see AD, that means adjustment. So we also include the adjusted version of model 1 to 5. We will introduce later how we did the adjustment. And in the end, we generate data in 3 different scenarios. Scenarios 1 is without confounders. So basically, if you remember, for the treatment variable, the probability of assignment is the p of s, and here we just assume is as constant 0.5. So it doesn't include any spatial information or covariate information, so it's unconfoundedness scenario. In the second scenario, we include x. So here is the scenario where x, the covariates, will influence both the treatment, and through the treatment, also the covariates themselves, they will influence y. So when you have this scenario where x influence both the treatment and y, x is called the confounders. And in this case, X are observed. So in the scenario 2, we have observed confounders. And in scenario 3, you can see that in the function for P of I's, it has the hidden covariates. So in this case, we are having the hidden confounders. So these are the 3 scenarios. Next slide. I have all the simulation results in my slides. For the first 2 scenarios, they are in my backup slide. And here I want to show the most complicated case where we have the hidden confounders and we want to see what would be the performance from our model. So when there are hidden confounders, the true form of the Quantile function is written in this format. You can find x1, x2, x3 to up to x6, and they are combined, multiplied with complicated functions. So it doesn't represent any real cases, but we intend to make it as complicated as possible. Like you can see, there are different number of the powers and multiplication with exponentials and something like that. So that's our intent, to make it complicated. And in addition, there are terms also from the hidden confounders, H1, H2, and H3. And in front of the T of S, which would be the treatment effect. So when T equals to 1 and T equals to 0, the difference will be 2 multiply S1 multiply tau minus 1/2 square, right? So that would be the true treatment effect, which is tau dependent and spatially varying, and is nonlinear. So this is our construct where basically the final target is to estimate this term in front of Ts very well, which is heterogeneous with regard to space and tau, and is nonlinear. So this is the most challenging scenario in our simulation study. Next slide. So first, on the left, we are showing the result, the arrow term, the log of loss of the predictions. So basically, we first want to see what would be the arrows for y. And on the right, we are showing the estimated arrow for the QTE. So we do have the spatial arrow also, but here we are averaging over space to see what is happening with regard to the quantile. And the arrows are shown in the log scale. And the first 2 simpler models, which include only the covariates and the spatial coordinates, they are shown in red and yellow. And the models with additional spatial features with different number of resolution spatial features are shown in the blue colors. So the darker the color, it means it includes more of the spatial features. And also there are dashed lines. So the dashed lines represent the models where we did spatial confounding adjustment. So here we are showing all the results from the 10 of our models. In particular, we see relatively lower error for the prediction y, the prediction for the quantile themselves on the left, and the estimation error for QTE on the right. And you can see clear difference between the different color groups, right? So the blue models, which include more complicated spatial features, they tend to perform better. Like the darker the blue color, the arrow tends to be smaller. And next slide. So in the previous slide, we were showing the estimated error or bias for QTE, which was averaged over space. And here we choose one quantile, and we want to see how is the spatial pattern of the estimated error for predicting Y. So the size of the dots is proportional to the error term themselves. And we can see in model 1 the patches of the dots are bigger, so the arrows are bigger, and we see quite clear patterns of the residues basically. And from model 3 to 5, they are getting the noise patterns are getting more random, and the relative size of the arrow themselves is getting smaller. And maybe next slide. So basically, previously we were showing the spatial patterns of the prediction themselves, and here we are showing the bias for the spatially varying quantile treatment effect. Also, we choose one tau level, which is 0.05. So it has similar patterns as the error for the prediction themselves. And basically, we were trying to show the magnitude of the error were decreasing with more spatial features. But probably here we are not seeing too many dots because they are too small. And maybe 2 slides back. Yes, please. And for the spatial patterns for the prediction error and the SQTE bias, we were choosing tau equals to 0.05. So it is basically the like vertical line on the very left. And another observation from this simulation study is the arrows tend to get bigger as they goes to the extremes, left and right tails, as you see in both of the estimations. So the arrows, that is one of the big observation we notice. So in particular, the scale for tau equals to 0.05 is increasing with regard to tau itself on the left figure. So you cannot see my mouse moving because Mary is helping me to control it. But you can imagine like on the very left tail where we choose 0.05 on the left. So the arrow increases a lot compared to the bug. Yeah, thank you. So let's go to the next. Yes. So in the application, we want to quantify the maternal smoking effect on the baby's birth weight outcome. In particular, if a baby was born with very low birth weight, it's a very dangerous scenario. It also influences their future health development. And here we are representing the birth weight based on the geolocations of where the mom live, basically. And if the dots are in red, which is not super obvious, it means it's very unhealthy. It is like a very low birth weight and it's dangerous. And this cutoff is at 2,500 grams. So it's about 2.5 kilo. So the low birth weight is an important risk factor, and we want to quantify the smoking effect from the mom of the outcome for the baby's birth weight, especially for the babies with low weight already. So this is our data set. So we have covariates about where the mom lives, the parents' social demographic features. So we have around 31 covariates. For example, using the same notation, the dimension for x is 31. And luckily for this data set, we have where exactly the mom lives. So we have the spatial coordinates. And here is the SQTE estimation result from model 1. In particular, so the color scale is not super distinguishable, but as you can see from the bar, it's always negative. So we see clear negative effect consistently for babies with low birth weight, which low we mean 0.05 quantile. And this is the result from model 1. So we have 30 covariates. So the dimension for x is not 31 but 30. And next slide, please. And also, based on our simulation study, the model 5 AD was the best. And here we are using the same color scale. So the reason the previous one was not super obvious was because we were using this bar as the standard. So the range for the other one was like within this total range. So the difference was not super obvious. But with our best model, which we include more spatial features, we can see clear spatially varying effect. So basically, there is huge heterogeneity over the space. Like the darker the dot, it means the effect is more severe, means the weight will be, the effect from the maternal smoking will be much lower. So in the worst case, it could be around minus 400 gram. That means if the mom smokes and if they live, for example, in the middle of North Carolina, which is the more severe area, the estimated effect can be quite negative. So here demonstrate like our model is able to capture the spatially varying quantile treatment effect. And in particular, we have 30 covariates, and in the model 5, in total, with 3 different spatial resolutions, we have 83 spatial features. So this is our model. And yes, that was all the important information from my paper. And if you are curious, you can check our paper on archive. And I do have backup slides for other simulation scenarios and the uncertainty quantification for our applications. And I'm happy for any discussion. And thank you for your attention.
Thank you so much, Yan. That's a really amazing piece of work. We have about 15 minutes for Q&A. If you have any questions, please feel free to unmute yourself or type it in the chat. I'll read those questions aloud so everybody can hear. What is the size of the, I guess, covariate matrix? You said 83 X's. How many samples do you have?
So I think I have around 10,000 data points. And they live on around 700 different locations. So there are different number of observations at each location. And we have 30 covariates. And in the most complicated case, for the spatial features, we are including 83 like spatial splines, basically, in addition to the longitude and latitude itself. Thank you.
So you have 1988 to 2002.
Mm-hmm.
Did you have a
So
time covariate as well? Time component?
um, we didn't consider time, and we tried to get as much information as possible. So we basically took the whole data set.
Any other questions? Jen, do you have a question?
Yeah, I think you mentioned the Gaussian process somewhere in your talk. So did you combine Gaussian process with a causal inference in some way?
So the question is, if I use Gaussian process in my modeling for the causal effect?
Yeah, pretty much.
So actually, we didn't. Only for the spatial features, we were inspired, of course, by the multi-resolution Wandland covariance matrix. So that's the only part which we use traditional spatial statistics, and all the rest are based on these neural networks with I-splines and M-splines, which can match the PDF and the CDF very well. So in the end, we didn't use much of the Gaussian process themselves, more like a general semi-parametric neural network-based framework. And the parametric part is only these I-splines and the M-splines. So no Gaussian process in the modeling themselves.
We
I
have
see.
one question from Eva. Eva, can you unmute yourself?
Yes. Hi, Anne. This is Murphy. I'm a postdoc at Wake Forest University, North Carolina. Thank you for your talk. Causal inference started to be something that I'm interested in recently, worked on some projects. So I do have a few questions, just so help me understand this method a little bit better, if you don't mind. First of all, I was wondering about the probability, especially in your application, probability of receiving a treatment. Is that estimated, or you set it just to be something constant and that's it?
So we didn't put too much detailed analysis based on the treatment probability, treatment assignment probability. So in our data in particular, it never violated the last scenario for the assumption. So we always have positive probability for the treatment assignment. So that's maybe a good feature from our model. So it was not a problem in our application, and it was also not a problem in the simulation itself, because we simulate probably 1,000 for each of the locations. So we didn't encounter this problem, but of course, in other applications, we need to check if the dataset itself will satisfy the last assumption on the positivity, right?
Mm-hmm. Yeah. I see, but you did have something in your simulation that said that your probability is equal to some kind of, and you gave it a function to it.
Yes. So to be specific, basically we are giving same probability weights the simulation, and in the application the weights are different, and it's basically in the end it's never zero, but the effect of the different probability assignment is reflected in the uncertainty quantification. If you, I think I have it in the backup slides. So it is only reflected in the uncertainty quantification, like the number of the different assignments are not super balanced on each of the location.
Yeah. Yeah. And then when
That's a
I
good point.
Yeah. Thank you. When I work with quantiles or extremes, or well, mainly with quantiles, what I read about then that there is this problem of quantile crossing, and especially when you add them with neural network that don't know about the ordering of the quantiles, and you do have the possibility of quantile crossing there. Is that something you have to account for in this setting, or how, and if so, how do you do that?
So that's a very, very important observation for quantile treatment effect, or in general quantile modeling. If you directly model the quantile themselves, of course, you sometimes face this problem for quantile crossing if you don't add additional constraint. But the benefit of our framework is that we didn't directly model the quantile themselves, but we were modeling the whole distribution. If you remember in the beginning, the semi-parametric construction is for the CDF itself, right? So if we have the whole CDF, we basically have the whole distribution, and you can do the inverse to get your tau at each quantile. So that is one of the benefit of this framework. So we don't have that problem from the beginning.
I see. Yeah, that's true. Okay, so you go about estimating the distribution, not the quantiles. You compute the quantiles from the distribution. Okay, yeah.
So I think it's this one, right?
Yes, thank you.
Okay, yeah, I remember that. Yeah. Okay, that makes sense. And then you did say something about splines, and then you have a set number for the splines. How did you go about finding that set number to use in your model?
Yeah, that's a very good question. We were also struggling, how do we want to decide how many multi-resolutional features we want. So we start from simple, and we adopt one principle from this paper. You can also see from this slide. So this deep Kriging framework paper. So we were really inspired by how they construct these spatial features, and how flexible it can be. And they mentioned like there's a principle, like rule of thumb, how you decide what is the number of splines you want to choose for each resolution. So basically, we have three setups for the first scenario, where we have only one resolution. It was around like less than 10, and for the second resolution is around like 30, and the last resolution is like more higher. So in total, it was 80 for the last scenario. So there is a particular function, like how many spatial features you want to choose as a function of the number of resolutions you are choosing. So if you check, there was a formula, like there's a direct like rule of thumb recommendation how we can choose this. And of course, that's not a very satisfying answer. And that's why we were testing in several scenarios. And we were seeing improvement by including more resolutions. So in the simulation, we see the errors were decreasing, but up to a limit. And it's also related to their computational power. So in this case, we don't want to, we don't have improvement with the increasing number of resolution, but we don't really want to make the model too complicated, since we only have maybe 10,000 data points. So this is also a trade-off. So there's no one answer principle, but whatever works well, and there's this rule of information is also important. So I recommend if you can check this paper also.
Yeah, for sure. Thank you. Appreciate that. Well, thank you very much, Ian. I do enjoy your work today. Appreciate it.
Thank you,
Yeah, thank you.
Eva. Maybe you and Yan can work on a paper together. So, any other questions? If there are no more questions, then I think that's about it for today. We will post the slides and also this video on our website. If you have additional questions for Yan, please feel free to reach out to her via email. I'm sure she will be very happy to continue the conversation. We will be posting announcements for our next seminar soon, so please keep an eye on your inbox and our website for updates. So thank you all for joining us today, and we look forward to seeing you next month. Bye-bye. Thank you, Yan.
Yeah, thank you, Mary.